So, hello, this is the first multibody dynamics analysis which we will attempt, and here our objective is to learn how the governing equations are automatically generated in a computer program. So in this case actually we are considering plane motion of pin jointed bodies. So if you look at this figure, so this is body 1, this is hinged to the ground, and about this point, about this axis going inside the paper at this point, about the axis going inside the paper at this point, it rotates. So this is rotation about an axis about this point, and this is body 2, this is hinged to body 1. So we will consider bodies like this, and if there are 3 bodies, so it will be like this. So this is hinge, this is pin, this is pin, and if you add further, if you add bodies, it will be pinned here. So these are pin connected bodies, and the first one is obviously hinged to ground, and we will analyze this to generate equations in this form, and will not write the equations. The equations will be generated in a computer program. So that is our objective. So the naming conventions which we are using is this. So this point is O, and all other hinges, so all other pins, so this is pin in body 1, so we call it P1. This is pin in body 2, so we call it P2. That means if this is P1, if this is P1, this is P2, and this here another body will be connected. So this is pin in body 3, so this is P3. Obviously pin 2 is shared by both body 2 and body 3. Pin 1 is shared by both body 1 and body 2. And this is the hinge point which we call O. And we assume that from O to P1, that is this line, the line connecting the hinge and the pin, along this will take the y1 axis. Why y1? Because this is the y connected to body 1. So this x1 and x1 y1 is fixed to body 1, and we have assumed that y1 is the line joining the hinge and P1. So x1 will be along this, and this x0 y0 is actually the coordinate system fixed to inertial reference. So x0 and y0 fixed to inertial reference, x1 y1 fixed to body 1, x2 y2 fixed to body 2. Again this y2 is actually the line joining pin 1 and pin 2. So these are the naming conventions which we are using. So, and this is the center of mass of body 1, so we call it G1. This is the center of mass of body 2, we call it G2. So from the first pin, which is hinge in case of body 1, so this vector from this pin to center of mass is R1, and here pin to center of mass R superscript 2, and these are the generalized coordinates Q1 and Q2 here, and for this again Q3, that is the relative rotations. Relative rotations means the rotation of the first body with respect to inertial reference. So this is the y-axis of the body, this is the y-axis of the inertial reference, the rotation is Q1, and this is the y-axis of body 1, this is the y-axis of body 2, rotation Q2. This is the rotation y-axis of body 2, this is the y-axis of body 3, so rotation Q3. So Q1, Q2, Q3, these 3 rotations are our generalized coordinates. And this vector, this O to G1 is R1, O to G2 is R2, and from O to P1 we will call it P1, P1 to P2, this vector we call P1. So P1 to P2, this vector we call P2, and this vector. So this is the convention which we are using, P3. And all the vectors will have components along the coordinate directions. So it can have components, suppose you take this R1 can have components along x1 and y1, as well as it can have components along x0 and y0. So, and as I told, our objective is to generate equation in this form, this mq double dot equal to f, and the inputs will be given rx1 ry for the two body problem. Rx1, that is component of r1 along x1 and y1. So they are constants because x1 and y1 are fixed to the body. Similarly, we have to give r2 along x2 and r2 along x2 and y2. So, and we have to give P1 along x1 and P1 along y1, and we have to give the forces, the active forces at center of mass of the body. So these are the active forces. Active forces at center of mass of the body. These are the active moments. Active moments or couple moments, whatever you call, active moments. And this is mass 1 of first body, this is mass 2 of the second body. This is moment of inertia about cm, about center of mass for the first body, and this is about center of mass of the second body. So we are first considering the two body problem because that is the simplest case, and that will help us understand how the computer program is to be written so that the equations are automatically generated. And once we write the equation in this form, then with the initial conditions are q1 q2 and q1 dot q2 dot, that is the initial position and initial velocity, and at t equal to 0, from that we will find out the subsequent motion. We will integrate the equation in time and we will find out the subsequent motion. So we start with the shifter matrix, and you all know that if this is x, y, and this is x dashed, y dashed, then what are the, so this is I dashed, this is j dashed, this is I, and this is j. So you know what is the relation between, I dashed, I dashed, j dashed equal to, if this angle is theta, this angle is theta, this is cos theta, sin theta, minus sin theta, cos theta, I, j. And with this we start. So this is the shifter matrix. In the next lecture we will see the shifter matrix in details. So the shifter matrix. So this is the shifter matrix between 1 and 0. So this is the unit vectors of 1. So the shifter matrix of 1, that is x1, y1 and x0, y0. So in the left hand side this is 1, and in the right hand side the unit vectors along 0, that is the inertial reference. So this is between the x1 y1 coordinate system and x0 y0 coordinate system. And as you know, this has got cos q1 because this angle is q1 between x1 and x0. So cos q1 sin q1 minus sin q1 cos q1. So this is the shifter matrix. Again, if you take 2 and 1, so the shifter matrix between 2 and 1. So this is the unit vectors of 2 and these are the unit vectors of 1. So now if in place of this again you write this, so this becomes the shifter matrix. This becomes the shifter matrix between 2 and 0. So this is S21 and this is S10. So S21 into S10 is what we call S20. So this is the shifter matrix. Now what is the derivative of I1 J1? See, I0 J0, I0 is along this, I0 is along this and J0 is along this. So they are unit vectors. So they have magnitude of 1 and the directions are also constants as they are fixed to the inertial references. But what about this I1 and J1? I1 and J1, they are magnitude wise they are 1 but their directions are changing. And when you take derivative of a vector whose directions are changing, the derivative is not 0. So what is, or not null. So what are the derivatives? So I dot, if I1 J1, you know this is the shifter matrix S10 into I0 J0. So if you take dot of this, then this will get differentiated, this two will get differentiated, but this will not get differentiated because these are fixed. So if you differentiate cos q1, you get minus sin q1 q1 dot. So q1 dot is common for all the terms. So this is what you get. Now, so now if you replace this I0 J0 by I1 J1, so then you have to bring in this. So because what is I1 J1? So we know that I1 J1 is this. So I0 J0 will be S10 inverse I1 J1. So here we can write that I0 J0 is equal to S10 into inverse I1 J1. And since this S10 is orthogonal matrix, the inverse is transpose. So what is the transpose of cos q1 sin q1 minus sin q1 cos q1? The first row becomes first column. So when you replace this by this, so this matrix comes in. So this first row becomes the first column and the second row becomes the second column. And this is nothing but S10 transpose. So S10 inverse is S10 transpose. So we get I0 J0 is equal to S10 inverse I1 J1, and this we get from the first relation. I0 J0 equal to S10 comes here inverse I1 J1. So I think this is clear to you now. So and this we call S10 dot. So I1 dot J1 dot is equal to S10 dot S10 transpose I1 J1. So now if you multiply these two matrices, so you get this q1 dot remains, and you get 0, 1, minus 1, 0, because if you go along this and along this, so minus sine q1 cos q1 plus sine q1 cos q1, so this is 0, and here minus minus, so sine square q1 plus cos square q1, and you get 1. So in this way you get this, and this matrix we call the omega 1 matrix, because this is 0, q1 dot minus q1 dot 0, and this we call omega 1 matrix, where omega 1 is q1 dot. So now we have seen what is the omega matrix. So omega can be kept as a vector. Omega can be kept, suppose omega 1 for 2D problems is along k axis. So omega can be kept as a vector, or it can be kept as a matrix. So since this is a 2D problem, all omegas, so this omega of body 1, omega of body 2, whatever, they can be, and they are all in the same k directions. So the vector are all in the k directions, and this is the omega 1 matrix. For matrix we will write like omega 1, that means omega of body 1 matrix. So omega can be written as a vector, or it can also be written as a matrix, and if it is written as a vector, the magnitude of the vector is q1 dot. And similarly, if we, so now you understand this, and now if you, what would be I2 dot J2 dot, that would be simply, in place of S10 it will be S20 dot S20 transpose I2 J2. So if it is I2 dot J2 dot, this would be I2 J2, and here we will get the omega 2 matrix. So this is the omega 2 matrix, and S20 is S21, this is S21, and this is S10. This we have seen, and if you multiply this, you get this. So S20 is this, and S20 dot S20 transpose is this. So this is the omega 2 matrix, where omega 2 is q1 dot plus q2 dot. So this is the angular velocity of body 2, and you know angular velocity of body 2 is q1 dot plus q2 dot, because we are taking this rotations as relative rotations. So this is, so total rotation, suppose you take body 2, then the total rotation about the inertial y naught direction is q1 plus q2. So the angular velocity of this body would be omega 2 q1 dot plus q2 dot. Now this convention we have already seen. O2, center of mass R1, and you can express R1 along x1 y1. So this is R1 x1 I1 plus R1 y1 j1. Similarly for R2, and these two hinge OP1, these two pins, hinge is also some sort of a pin. So OP, so OP1 is this, and P1 P2 is this. See, here we have all taken components with the body fixed references. So x1 and y1, they are constant because they are fixed to body 1. x2, px2 and py2 are constants. Here px1 and p1 x1 and p1 y1 are constants, and here p2 x2 and p2 y2 are constants. R1 x1, R1 y1 are constants. R2 x2, R2 y2 are constants. Why are they constants? Because they are fixed to the body, so they are not changing with time. But which is changing with time? This, the unit vectors are, the direction of the unit vectors are changing with time, but these magnitudes are not changing with time. The direction of the unit vectors, again I2 J2 is also changing with time, but these magnitudes are not changing with time. So you have to carefully check which one is changing with time and which one is not. Now we come to the most interesting part, that is the velocity of center of mass. So suppose this body, we want to find out the velocity of the center of mass. So V1, as we know, is omega cross r. So for this body, omega 1 is the angular velocity and the direction is k1. So k1, k2 all are same because this is plane motion and this is r, r is this. Remember, when we write this expression v equal to omega cross r, if it is a vector expression, then we are free to express these vectors along any coordinate system. So here we have expressed the r1 vector along x1 and y1. So if you perform the cross product, you get this, and that means if you write v dash dash, again here see, you are taking components of v1 along x0 and y0. That means along the coordinates fixed to inertial reference. So v1 x0, v1 y0, I0, j0. So if you multiply this, this becomes v1 x0 I0 plus v1 y0 j0. So this is a vector. So and this vector is this. But these vector, the components are expressed with respect to I1 and j1 because this is this. So if you write it in matrix form, so this vector to this vector, this means minus r1 y1 I1 plus rx plus r1 x1 j1. So now what we do, we simply express this using the shifter matrix and we write it like this, and this is known to you. So now in the left hand side we have this and the right hand side also we have this. So we can drop it and we can write this matrix equation. So whenever you write a matrix equation, so you have to check that the unit vectors are same on the left and right hand side. So again for body 2, see, the velocity of the center of mass is velocity of point P plus velocity of g2 with respect to p1. So these are the two components. So this is the velocity of p, so this is velocity of p, and this is velocity of g2 with respect to p. So this is omega 1 k1 cross p1 plus omega 2 k1 and k2 are all the same, so k2 cross r2. So this is the first term and this is the second term. So cross products, that means since you have already seen how the cross products can be expressed, it can be expressed like this. It can be expressed like this. So the first term, this is fixed to 1, p1 y1. So in place of r1 x1 we are getting p1 x1. In place of r1 y1 we are getting p1 y1. So simply in place of r1 y1 you put this, r1 x1 you put p1 x1 s1. So this is the first term, and for the second term the omega is omega 2 and r is, this r is expressed in I2 J2. So what is the shifter matrix between I2 J2 and I0 J0? That is S20. So you use this. So this is the velocity of body 2. So now if you drop this I0 J0 from both the sides, you get this vector equation. So now if you combine this one and this together, so if you combine this, so this is for body 1, this is for body 2. So for body 1 you get omega 1 into this and omega 2 into 0. null. So omega 1 into this, because that is the angular velocity of body 1, sorry, that is the center of mass velocity of body 1, this one, omega 1 this into this, so omega 1 this into this. And what is the velocity of body 2? This is omega 1 into this is actually, so omega 1, when you multiply with this, you get the angular velocity of point P1, sorry, the velocity of point P1, and when you multiply omega 2 with this, we get the relative velocity of G2 with respect to P1. So this is the first term. So when you omega 1 multiplied by this is the first term, and omega 2 multiplied by this is the second term. So just do a little bit of matrix algebra and you please convince yourself. So also you can see the dimensions of these matrices. Then check. So this is one row, 2 column, 2 row, 2 column. So it will be 1 row, 2 column, 1 row, 2 column. The first one will remain and the last one. Similarly, this is 1 row, 2 column. So there are 1 row and 4 columns. Here also there are 1 row and 4 columns. So this is 2 into 4. So 2 row into 4 columns, 2 rows into 4 columns. So 1 into 2, 2 into 4, you get 1 row and 4 columns. So this is 1 row, 4 columns. So the left hand side and right hand side match. So now if you call this as SR1, that means minus R1Y1 R1X1, you called SR1, and this you called SP1. So this would be SR2, SR2. This would be SR2. So SR2, SR2. So you write it like this. So you are getting a nice pattern, and you know that omega 1 is Q1 dot and omega 2 is Q1 dot plus Q2 dot. So this is Q1 dot Q2 dot this matrix. So if you multiply this to this, you get this, and if you go again through this and this, you get this. So this is Q1 dot, and you call it T omega Q. Omega took the transformation matrix between omega and Q. So T omega Q. So this is the transformation matrix between omega and Q. So you replace this omega 1, omega 2 by Q1 dot Q2 T omega Q. So this is what you get. So Q1 dot Q2 dot T omega Q, this, and this Q1 dot Q2 dot into this matrix, this total thing we called VPD, or the partial velocity matrix. Now why do we call it the partial velocity matrix? We'll examine in the next lecture. Now partial velocity matrix. So we have seen that this V1 x naught, V1 y naught, V2 x naught and V2 y naught, this can be written as Q1 dot Q2 dot into a matrix of partial velocity, or the partial velocity matrix. So what are these? This is center of mass velocity for body 1, x component along x naught, that is inertial x direction, y naught inertial x y direction, and this is velocity of center of mass of body 2, inertial x direction, velocity of center of mass of body 2, inertial y direction. Q1, Q2 are the generalized coordinates. So why is it called the partial velocity matrix? Because some partial differentiation is involved. So this is the velocity. So velocity term is okay. So partial means we are actually taking the partial derivative of Q1, partial derivative of this velocity, center of mass velocity, with respect to q1 dot and then q2 dot. Suppose we take the partial derivative of all these quantities with respect to q1 dot and we club it in a row. Then what happens? See, this VPD consists of T omega q and this. So none of these two matrices, they contain q1 dot or q2 dot. So if you take a partial derivative with respect to q1 dot, only this one will get differentiated and this will become 0 because you are taking a derivative with respect to q1 dot. So it will be 1 0 VPD. So that means the first row of VPD, because when this goes in this direction, so the second row will become 0, only the first row. Second row will be multiplied with 0, only the first row will be multiplied with 1. So this gives you the first row of VPD. And if you take derivative with respect to q2 dot, then what happens? So this derivative of q1 dot and q2 dot, this will become, if you take derivative, then this will become 0 and this will become 1. So only the second row of VPD remains. So now if we combine the derivative with respect to q1 dot in the first row and the derivative with respect to q2 dot in the second row, that will give you first row of VPD and then second row of VPD. So what is this then? That is nothing but VPD itself. So what happens in, how can we extend this in 3 pin jointed bodies? So here there will be center of mass velocity of body 1 in x naught y naught, center of velocity of body 2 x naught y naught, center of velocity of body 3 x naught y naught. So this body 3 has come. Now first omega 1, this SR1 S10, which is the velocity of this omega cross, this is the velocity of this center of mass G1 and this is R1. So this is omega 1 cross R1. And what is the center of mass velocity of this? If this is the center of mass of body 2, this is R2. So this is the velocity of this point, this is P1, velocity of this point is SP1 S10, then this SR2 S20 will be multiplied with this. So it will be this omega 1 into this plus omega 2 into this. And for body 3, it will be velocity of this, then velocity of P2 with respect to P1. So P1 with respect to O, this omega 1 into this, you get the velocity of this. Then P2 with respect to P1, so you get omega 2 with respect to omega 2 of this point with respect to this point. So this is this, then omega 3 into this. So this is SP3 to S30. So just notice the pattern. So if you keep on increasing the bodies, then the terms will be added and this matrix will get expanded. So again the and what would be the this is not VPD, because here it is in terms of omega 1, omega 2, omega 3. So you have to write it in terms of q1 dot, q2 dot, q3 dot, then comes your T omega q, and then this term will come. So if you combine this with this, you will get VPD. So what is T omega q in this term? In this case, omega 1, omega 2, omega 3 is q1 dot plus q2 dot, q1 dot plus q2 dot plus q3 dot. So this is the T omega q matrix. So VPD is T omega q into this. So this is a 3 into 3 and 3 into 6 matrix. So this is a 3 into 6 matrix. VPD is a 3 into 6 matrix. It has to be like that because this 3 into 6. So this is 1 into 3, 1 into 3, 3 into 6. So 1 into 6, and here there are 6 columns. So this is the partial derivative. This is the partial velocity matrix for in case of 3 pin connected bodies. So here in the first row, so T omega q to 3, it's 3 by 3, this is 3 by 6, so VPD is 3 by 6. So in the first row there would be the derivative of 6 components of 3 velocities, 3 center of mass velocities, body 1, body 2 and body 3 with respect to q1 dot. In the second row it will be with respect to q2 dot, and in the third row with respect to, this is q3 dot. This is q3 dot. Maybe a mistake due to copy pasting. So this is q3 dot. So as you know, this is first row of VPD, this is second row of VPD, and this is third row of VPD. Now what about the partial angular velocities? So here there are 2 angular velocities, omega 1 and omega 2, which can be written like this for 2 bodies. And if you take del omega 1 del q1 dot and del omega 2 del q1 dot, del omega 2 del dot, so here so if you do this, so that means this matrix will get differentiated by q1 dot. So q1 dot means 1, 0, that means this itself is, so this is first row of WPD. So if you call this WPD, then just see that if you take the derivative of with respect to q1 dot, then it is 1, 0 WPD, that means the first row of WPD. And if you take derivative of these 2 terms with respect to q2 dot, then you get 0, 1 WPD, that is the second row of WPD. So partial angular velocity is WPD is, and that is 1101. So you have noted that WPD and T omega q are same in this case. WPD for this case, for plane motion of pin jointed bodies, for this case WPD is T omega q. So now that means this is the partial angular velocity. That means the angular velocities are differentiated with respect to q1 dot and q2 dot. So partial angular velocity is WPD. So for 3 bodies it would be simply this. Here you notice that the center of mass velocity has 2 components, one along x direction and one along y direction, but omega has simply one component, it is about z, and z for all bodies are same in plane motion. So for omega only 2 terms are coming. So So two terms, one getting differentiated by q1 dot and one is getting differentiated by q2 dot. So for two bodies the partial velocity will be one row, so two rows, two columns. So this is two rows, two columns. And for three bodies it will be three rows, three columns. Now we come to, so yes, now our objective is to find out the acceleration of center of mass. But before that, let's see how can we write the vector cross product in matrix notation. We have already done so while calculating velocity. We did omega cross r, and omega cross r has been expressed in matrix notation. But here we see that there is another way of doing so. So let's see what is that. Suppose you have omega k cross rxi plus ryj. So let ij be fixed to the body, and rxy and ry are components along the body fixed x coordinate and body fixed y coordinate. But we are not putting any superscript here. This is applicable for any body. So if you do that and if you evaluate the cross product, then you can show that this is minus ry rx I j. So this we have already seen. That means minus omega ryi plus omega rx j. So this we have already seen. So let us call it cx cy I j. Now suppose we again pre-multiply this by omega k. So this is and for this we put cross or we write it like this. So this can be again written as omega minus cy cx ij. This we have done before, and following the same procedure we can write it like this, but we will not do this. Instead we'll write this as omega cx cy so we'll write it like this. See, we are getting the same final product because this is minus omega cy I plus omega cx j. This is also, if you multiply this, so this gives you minus cy omega, and here you get cx omega. So this and this are same, but during the second cross product we will follow this way of expressing the cross product in matrix notation. So we will not take this form, rather we will take this form. So now already we know that Cx is minus omega Ry and Cy is omega Rx. So here we put omega Cx is minus Ry, omega Ry, Rx 0, omega minus omega 0 I. So the two cross product are expressed in different ways, but this is what we get finally. And you know that this is SR and this is the omega matrix. So now see, if you try to find out the center of mass acceleration of body 1 with respect to the inertial frame unit vectors, so then this can be written as this. Now this is omega cross R for body 1 and alpha cross R for body 1. So see here there are double cross products. So just as in the same way as what we did here, so we are writing it as omega 1. Here only the difference is we are putting the superscripts 1 for body 1. So this is what we get for the first term, and for the second term we are using our previous way of expressing cross product. Here there are two cross products, that's why for one cross product we are using the previous way, and for the other cross product we are expressing the cross product using omega vector. But here again we are using the previous way, so alpha 1 k cross R, so this is this. So now, so here this is omega 1, this is SR1, this is the omega 1 matrix, this is the omega 1 matrix, and this is since this is with respect to I1 J1, because RY1, R1 Y1, R1 X1 are expressed in coordinate system X1 Y1 and the unit vectors are I1 J1. So this I1 J1 has to be converted to I0 J0, so it is pre-multiplied with S10, and for this again S10. So if you notice carefully, this is actually the normal component of acceleration and this is actually the tangential component of acceleration. So now here if you drop the I0 J0 from both the sides here, so you get this relation. Now this is the center of mass acceleration. Now what is the acceleration of this point P1? You know the vector from O to P1 is P1. So in place of R1 you would be simply using P1 to get the acceleration of this point. Now what is the acceleration of this point? So that would be the acceleration of P1 plus omega cross R plus alpha cross R. here omega and alpha will be, omega, alpha and r will be those of body 2. So here you see the center of mass acceleration, that means the acceleration of this point is actually the acceleration of this point plus omega cross, that means this is acceleration of g2 with respect to p1, that is omega cross r plus alpha cross r, but here omega, alpha, r, they are all for body 2. So whatever we have got for body 1, there the 1 superscript has to be replaced by the superscript 2, and exactly that's what we have done. So the center of mass acceleration is this. This is for the normal component and this is for the tangential component of normal of a g2 with respect to p1. This is the normal component corresponding to the normal component, and this is corresponding to the tangential component. So now if you write it side by side, then this is what you get. So omega 1, omega for body 1, this is omega 1 into this, omega 2 into 0. So this is omega 1 into this, that means omega cross r for body 1. So this is the normal acceleration. If you multiply this with this, you get the normal acceleration for body 1, and if you multiply this with this, you get the normal acceleration for this is normal acceleration for point p1, and this is the normal acceleration of the point g2 with respect to p1. Now what is this? This is the tangential acceleration. This is the tangential acceleration of the center of mass g1, because alpha 1 into this, alpha 2 into this, and if you multiply with this, this first term is the tangential acceleration of p1, and the second term is the tangential acceleration of g2 with respect to p1. So this is what you get, the acceleration expression. And if you replace omega 1, omega 2 in terms of q1 dot and q2 dot, you have introduced the t omega q matrix in between, and alpha 1 is q1 double dot and alpha 2 is q2 double dot. That is also related to q1 double dot and q2 double dot using this matrix, because if omega 1 omega 2 is equal to omega 1 omega 2 is equal to q1 dot q2 dot t omega q, then if you take derivative once again, double derivative, and here this is just a matrix containing ones, so here there will be no dot will come, so no derivative of this matrix has to be done. So this is simply this. That means if you make it alpha 1 and alpha 2, so this. Okay, so now you put, so I think I could explain this. So if you take derivative of this and derivative of this, then this will get differentiated. This is the matrix of ones, so 0 and ones. So if you want to keep this fixed and you want to take derivative of this with respect to time, you will get zeros. That means if you want to add a term, so q1 dot q2 dot T omega q dot, that will simply give you 0. So this term is not required. So this is what you get. So here this is the second term. So now this is actually the acceleration expression. Now if there are 3 connected bodies, so this for body 1, body 2, body 3, body 1, this is body 2, and this is body 3. So see, this is the normal acceleration of P1, this is the normal acceleration of P2 with respect to P1, and this is the normal acceleration of G3 with respect to P2, and this is the tangential acceleration of P1, this is the tangential acceleration of P2 with respect to P1, and this is the tangential acceleration of P3 with respect to P2. So just notice the pattern in this. Okay, so let us stop here. So let us first start with some corrections. So here actually in the figure, yeah, the directions of x-axis were not in this direction but in the other direction. Yeah, it is in this direction. So let us make it blue. So this is actually x1 and this is x2. So the previous x1 and x2 goes, and this is not x0, x0 in this direction. Yes, and then as we have mentioned that these are center of mass acceleration components, x0 component and y0 component of body 1, and x0 component and y0 component for body 2. So this 2 you will get when you multiply omega 1 with this and omega 2 with this, which is 0. So omega 1 in this with this will give you the normal component of acceleration, and alpha 1 multiplied by this and alpha 2 multiplied by this, which is 0. Alpha 1 multiplied by this will give you the tangential component of the center of mass acceleration of body 1. That means center of mass acceleration component, one in the normal direction and the other one in the tangential direction. So, and the normal direction, the normal acceleration when you resolve in x0 and y0, that is what you get if you multiply this with this, or omega 1 with this, and alpha 1 and alpha 2 when you multiply with this is 0, so alpha 2 will be multiplied with null, and alpha 1 multiplied by this is the tangential acceleration when you resolve it in this and this direction. Similarly, if you go to this, then this is actually the normal component. When you multiply this omega 1 with this, that will give you the normal component of acceleration of point P, that means in this direction, and this will give you the normal component of P in the tangential direction, that means in this direction. Then what about when you multiply with omega 1 with this, you get the normal component of P1, and when you multiply alpha 1 with this, you get the tangential acceleration of P for body 1 or P1. Now if you multiply omega 2 with this and alpha 2 you get with this, you get respectively the normal component of P2 with respect to the normal component of G2 with respect to P1 and the tangential component of G2 with respect to P1. The normal component of G2 with respect to P1 and the tangential component of G2 with respect to P1. So this is the explanation of the terms. Similarly, for this, suppose for this 3-body problem, so omega 1 into this is the normal component of acceleration of P1, omega 2 with this the normal component of acceleration of P2 with respect to P1, omega 3 into this the normal component of center of mass of 3, that is G3 with respect to P2, because this is SR. Similarly, alpha 1 multiplied by this is the tangential component of point P1. Alpha 2 multiplied by this is the tangential component of P2 with respect to P1, and alpha 3 is the center of mass of the acceleration of the tangential component of acceleration of the center of mass with respect to P2. So these are the terms. Now, so what is the inertia force? Inertia force is minus m1 for 2-body problem, minus m1 a1 x naught minus m1 a1 y naught. So this is for body 1 and this is for these two for body 2. So that means simply this multiplied by this diagonal matrix, and this we have already got as this here. So this we have already got as this. So here in place of this we simply put these two terms, one this and one this. One this term, one this term for the normal components, and one this term for the tangential components. And let us, other than the q1 dot, q2 dot and q1 double dot and q2 double dot, let us call it a1 and let us call it a2. Similarly, that means this now, the inertia force now becomes this into this. Actually what we have done, we have removed these minuses and we have brought in a minus sign at the beginning. So now what about the inertia moments, that is acceleration into mass moment of inertia about center of mass, again plus plus this becomes this, and this we call A3. So this is this. So now we get the inertia forces and inertia moments. Now if we again look at the equation as in our previous video on Keynes dynamics, so we will see this is the partial velocity matrix, this is the active force vector, this is the inertia force vector, this is the partial angular velocity, this is the active moment about Cm, active moment, rather you can say Cm, you can omit. Active moment about Cm, we mean that all the forces are brought to the Cm and the resulting moment, because couple moment in rigid body can be shifted anywhere. So this means when all the forces, all the externally applied forces are brought to the center of mass, this is the total couple moment, and these are plus the externally applied couple moments, and these are the inertia moments. So what we do actually, we take the partial velocity, this, let us put some color, yeah, so this into this plus this into this plus this into this plus this into this, again this into this plus this into this plus this into this plus this into this. So then plus this into this plus this into this plus this into this plus this into this equal to 0. So that gives you the first equation, and when you repeat that for this, the second row of this with this and this, the force part is complete. Then the second row of partial angular velocity, with this and equate it to 0, you get the second equation. So this is what is the first equation, and this is the second equation. And when you write it in matrix form, the inputs I have already discussed, this becomes VPD into all the external forces acting on the center of mass plus all the couple moments, WPD, that means partial linear velocity multiplied by all the forces acting at the center of mass, plus partial angular velocity in all the moments acting on the center of mass, plus partial velocity into the inertia forces plus partial angular velocity into the inertia moments equal to 0, 0. These are the two equations combined. Now these terms are coming from the externally applied forces and couple moments. So we call it F external. And we know this term is, okay, let us go back. Yes, we know this is this minus this. So the column vector is transpose of this is A1 transpose minus A1 transpose column vector Q1 dot Q2 dot minus A2 transpose column vector Q1 double dot Q2 double dot, and exactly that's what has been done. BPD A2 transpose plus WPD A3 transpose Q1 double dot Q2 double dot. So this is coming, yes, this first part is coming from the first term in the acceleration, linear acceleration. This first term is coming due to the first part of the linear acceleration, and the second term is coming due to the second part of the linear acceleration, and this part is coming for the angular acceleration. Okay, so let us have a look again. So this is the first term in the linear acceleration, second term in the linear acceleration, and the single term in angular acceleration, or angular inertia force, you may say, angular moment, inertia moment rather. So okay, let us change our terms a little bit. Okay, let us call this is actually the first part of inertia force. This is the first part of inertia force, this is the second part of the inertia force, and this is the inertia moment. So when you take transpose of the left hand side, this gets transposed and this becomes column matrix. So this comes forward, get transposed, and this goes this side and becomes column vector. So same for this. So if you just substitute, you can do the substitution on your own, and you will find that this is one term, the first part of the linear inertia force. Here this is the second part of the linear inertia force, and this is the inertia moment. So now if you combine these two terms and you call it F, and if you combine these two terms and call it M, since q1 double dot and q2 double dot are here, so you get equation in this form, mq double dot equal to F, and that is exactly, or you can write it like this, you can remove this, double dot equal to M. So this is the equation which was our objective, and where F external is from the externally applied forces and the externally applied couples. This is F. This contains time dependent terms, functions of q1 and q1 dot, and q1 double dot is separated and q1 double dot is only here. So q1 double dot is only here. M also contains time dependent terms, q1 dependent terms, and q1 q terms, q dot terms, and but q double dot terms will not be there. So in M there will be time dependent terms, q dependent terms, and q dot dependent terms, and in F also there may be t dependent terms, q dependent terms, and q dot dependent terms, but q1 double dot terms are all here, because in the acceleration expression you see, if you see the acceleration expression, all double dot terms are here and here. Nowhere is there any double dot term. So double dot terms separate out, and M is actually the coefficient matrix of double dot terms. But M itself may contain T, Q1, Q2 terms, Q1 dot, Q2 dot terms, M may contain. Similarly, this F is a 2-row 1-column vector, and it may contain T terms, Q1 terms, Q2 terms, Q1 dot terms, and Q2 dot terms. So, and so all these what we have discussed here, they are the main references for Farida Amiruj's book Fundamentals of multibody dynamics theory and applications. Thank you.